Hello everyone, this is Dr.V Madhavi, Associate Professor of Chemistry, BVRIT Hyderabad College of Engineering for Women. Today, we will go with basic principles of electrochemistry which can be useful for the next coming topics. So, what is this electrochemistry? Electrochemistry is the science dealing with transformation of electrical to chemical energy and vice versa. Transformation from electrical energy to chemical energy to electrical energy. So, when there is conversion from chemical energy to electrical energy, we call such kind of cells as electrochemical cells. If there is conversion from electrical to chemical energy, the kind of cell is called electrolytic cell. So, when there is a chemical energy to electrical energy, chemical reactions happen by liberating and absorbing electrons. So, liberation of electrons, absorption of electrons. So, in an electrochemical cell, it contains two parts, anode and cathode. This can be anodic half cell. This can be cathodic half cell. The two half cells combine to form a complete cell. And at anode, there will be loss of electrons, and at cathode, there would be gain of electrons. So, in the same electrochemical cell, at anode, there will be loss of electrons. These electrons will be moving from anode to cathode, and at cathode, the electrons are gained. So, as the charge is moving, electrons are also charged particles. The oxidation reactions and reduction reactions are happening. That is, we know that loss of electrons is oxidation, gain of electrons is reduction. We call reactions, the name of reaction we call it as redox reaction. What is this redox reaction? In the same chemical reaction, both oxidation and reduction takes place. We cannot see individual reduction reaction or individually oxidation reaction in a single reaction. We can see both oxidation and reduction happening in a single reaction. Such reactions can be called as redox reactions. This electrochemical cell having anode and cathode, both oxidation and reduction takes place. So, this system is called as redox system, where both oxidation and reduction takes place simultaneously. So, you can see here, loss of electrons is oxidation, gain of electrons is reduction. We can consider an electrochemical cell having zinc, metal, and its some zinc electrolyte solution at anode. This can be at anode, and at cathode, let us take copper with its electrolyte copper. Any copper salt solution can be considered as cathode. As we discussed, at anode oxidation takes place, that is, zinc liberates electrons. There is loss of electrons at zinc. The copper ions present in the electrolyte takes up these two electrons, become copper. You can see zinc is becoming zinc plus 2, copper ions are becoming copper. So, this would be reactions taking place in the galvanic cell when you take zinc and copper as different two electrodes. Now, as at zinc, oxidation takes place, that is, it is the responsibility of zinc to reduce copper ions. Now the zinc is able to reduce the copper. Similarly, in presence of zinc, copper is taking up 2 electrons and undergoing reduction. It is able to oxidize zinc. So, zinc undergoes oxidation, copper undergoes reduction. So, since the two reactions happen mutually, in the presence of zinc, copper undergoes reduction. In the presence of copper, zinc undergoes oxidation. So, we call it as zinc can also be called as a reducing agent. It undergoes oxidation, but it reduces copper. Similarly, copper can be called as oxidizing agent. It is oxidizing zinc. Copper undergoes reduction, but it is oxidizing zinc, so it is oxidizing agent. Oxidizing agent means what? It lets another substance to be oxidized. Reducing agents means it lets another substance to be reduced. Zinc is letting copper to be reduced. Copper is letting zinc to be oxidized. So, copper can be called as oxidizing agent. Zinc can be called as oxidizing agent in the reaction. So, you can see here the simple diagram for galvanic or voltaic cell, where electrochemical cell reactions takes place, where also the oxidation and reduction happens, where the spontaneous reactions are happening within the cell. So, because of flow of electrons, there would be development of voltage or current. So, we can say because of the chemical reactions, electrons are liberated, and the flow of electrons, we call it as electricity. So, finally, chemical energy is converted to electrical energy. So, here you can see in this picture, instead of placing voltmeter or ammeter to measure what amount of voltage is produced from the galvanic cell reactions, we can also place a bulb here. As anode is liberating electrons, the electrons will be moving from anode to cathode. The movement of electrons can be measured also by glowing this bulb. So, this would be the pictorial representation of electrochemical cell, voltaic cell or Daniell cell. So, as we discussed, zinc electrode in zinc electrolyte solution, we can take either of the salt solution. It may be zinc sulfate, zinc chloride, zinc nitrate, anything. This is a cathodic half cell. The electrode is copper. Its electrolyte is copper sulfate solution. So, what happens at anode? Zinc undergoes liberation of electrons. So, what happens? The zinc metal undergoes oxidation, liberating the zinc plus 2 ions into this electrolyte. Similarly, at the cathode, the electrons are liberated from the zinc electrode. The electrons are moving towards the cathode. And at cathode, we have copper electrolyte, Cu2 plus ions. The Cu2 plus ions take up 2 electrons. See, there are Cu2 plus ions in the electrolyte. Take up these 2 electrons and form copper. Cu2 plus take up 2 electrons and form copper. That is, the copper is deposited on the electrode. But on the anode, what happens? Zinc is liberating zinc plus 2, which is moving into the solution, electrolyte. So, what is happening at anode? Zinc is dissolving in the form of zinc ions into the electrolyte. We call this as dissolution. Because Zn is converted to Zn plus 2. Zn plus 2, once it is formed, it may be nowhere, it can be onto the electrode. Instead, it moves to the electrolyte. So, Zn is converted to zinc ions, that is dissolution happened. And what happened at cathode? Copper ions at the electrolyte are taking up the 2 electrons. The ion is converted to metal. So, once the metal form, it will be deposited on the electrode. We call the deposition. Dissolution of zinc happens at anode. Deposition of copper happens at cathode. And we have seen a salt bridge. This is the salt bridge here. What is the function of this salt bridge? Let us see. The salt bridge, the role of salt bridge in electrochemistry is crucial. That to electrochemical cell, it is highly significant. If the salt bridge is not present, what happens? Let us see. So generally, the reactions are happening inside the electrochemical cell. Zinc undergoing oxidation, copper undergoing reduction. The reactions happen to reach the equilibrium. The reactions need to maintain certain time. It should not, the reaction time should not be either rapid or slower. So if there is no salt bridge, the rapid running of reactions takes place. The presence of salt bridge, its significance is it is preventing the rapid reaction time to reach the equilibrium. The other important function of salt bridge is it prevents mixing of two solutions. So the electricity is produced by the movement of electrons from anode to cathode. We can also see zinc ions, sulfate ions, copper ions, etc. in the electrochemical cell. These zinc, copper ions, cations and anions can also mix through the electrolyte solution. It should not happen. So this is prevented by the salt bridge. The role of salt bridge is preventing the mixing of two solutions. If salt bridge is the third significant role of salt bridge is it prevent the further reaction and hence production of electricity. So if there is mixing of two solutions, that is zinc is moving towards cathodic electrolyte, cathodic half cell, copper ions are moving towards anodic half cell, what happens? The mixing of solutions takes place which may create the positive and negative charge accumulation, can be a kind of potential developed, that is junction potential, that prevent actual redox reaction to produce electricity. So this junction potential if developed, we don't get the voltage or current, that is actual redox reaction do not happen. So we need to avoid this junction potential. The junction potential is developed due to mixing of the two solutions. So this salt bridge prevent all such errors. One is rapid running of reactions, mixing of two solutions, prevention of junction potential which inhibits further redox reaction. The salt bridge generally consists of two types. One is glass tube bridges. The salt bridge contains some gel plus a salt. It may be potassium iodide or sodium sulfate. Filter paper bridges. The salt bridge is also made up of filter paper bridge which consists of filter paper and sodium chloride or potassium chloride. Cell potential. So there is a cell potential which is a driving force to develop this movement of electrons from anode to cathode. So electrons should flow from anode to cathode. The flow of electrons should be derived from some external force. That external force is called cell potential. This is measured in terms of voltage. The cell potential should be always positive. It should not be negative or zero. It should be always positive. So how to calculate this cell potential? Otherwise we call it as electromotive force. E cell. Electromotive force is potential at cathode minus potential at anode. The difference in potential, we call it as potential difference of two electrodes, can be considered as E cell, which should be always positive, should not be negative or zero. So we also have one more term in the electrochemistry, that is standard electrode potential. In a half cell, that is cathodic half cell or anodic half cell, we have the metal which is immersed in its own electrolyte solution. Considering the concentration of electrolyte solution, if the concentration of electrolyte solution is 1 molar, the potential developed at any respective electrodes is called standard electrode potential. We have a metal dipped in its own electrolyte. If the electrolyte concentration is 1 molar, it can be called as standard electrode potential. If the electrolyte concentration is not equal to 1 molar, means it may be 0.1 molar, 0.5 molar, 2 molar or something, not equal to 1 molar, the potential developed can be termed as simply electrode potential. Standard means when the electrolyte concentration is unimolar, 1 molar. If the concentration of electrolyte is not unimolar, we call it as simply electrode potential. So the standard electrode potentials always represented as E naught. Cell potential, we term them as only E. So this naught O represent as standard values. So for all kinds of metals, it may be zinc, lithium, potassium metals, the standard electrode potentials are developed or determined and are represented in a series, electrochemical series. So the electrochemical series consists of list of metals, lithium, potassium, sodium, zinc, copper, silver, aurum, etc. So all the metals with their standard reduction potentials are listed out. The list is known as EMF series. So through this EMF series, we can calculate EMF produced. E equal to E cathode minus E anode. We have the formula to calculate EMF of this cell. To calculate this EMF, we need the EMF series, that is standard reduction potentials of each and every metal. The metal through which metal we are going to construct an electrochemical cell, take the SRP values, that is standard reduction potential values of those metals, substitute here in this equation, you get the theoretical EMF of this cell. So now how to represent galvanic cell theoretically? So we have represented galvanic cell diagrammatically having the metal, electrolyte, etc. Theoretically, how to represent the galvanic cell? So we have two half cells, anodic compartment, anodic components contain anode and anodic electrolyte. So anode should be always placed at left hand side. Cathode should be always placed at right hand side. So what the anodic half cell consists actually? Both anode and its electrolyte, zinc and zinc sulfate. So zinc and zinc electrolyte should be placed towards left hand. Similarly, copper, that is cathodic components, copper and cathodic electrolytes are placed towards right hand side. So the metal is separated from its electrolyte by a single slash. Similarly, at cathode, metal is separated from its electrolytes from a single slash. Then this is salt bridge, which is separating two half cells. The salt bridge is represented by double vertical lines. Single vertical line represents the anodic metal and anodic electrolyte. Double vertical line represents salt bridge, separation of anodic and cathodic half cell. So you can represent the concentration of zinc electrolyte you have taken in your electrochemical cell and copper electrolyte present in the electrochemical cell. So for example, you have taken 0.5 molar zinc sulfate solution, 0.05 molar copper sulfate solution. Now how to represent? Towards left hand side, you should have anodic metal and its electrolyte with its concentration. Towards right hand side, you need to have cathodic electrolyte and its concentration. And these two half cells should be separated by salt bridge. This is anodic half cell. This is cathodic half cell. double vertical line represent salt bridge. Thank you.